Okay, so we will continue chapter 1. So again, as we discussed, so we have thermodynamics, Boltzmann, we have Ehrenfest. So these two guys were like killed themselves almost because of the fundamentals of thermodynamics, and this is what we're gonna start today. So again, today we have chapter 1. Okay. So today again we have the chapter 1. Just to remind you, we have 6 points we need to cover in chapter 1. Previous lecture we finished the first 2 points. So we started with, we make a quick revision of the dimensions and units, and we start to talk about the importance of engineers' roles in the energy, what it means by energy, where sustainability obtained, what is the relation between energy, sustainability, and these things. So hopefully today we can finish points 3 and 4. So these 2 points we will start with give a quick overview in the history of thermodynamics, how it's developed until we have it right now. And then we will explain some of the basic concepts and terminology. And these basic concepts are very important because in every chapter you will hear the same like items or terms that you will be repeating. So it's very important that you understand what is meant by each of these concepts that you will study. So let's start with the first one. So thermodynamics. So it basically appears because of our need to power everything. So before, like steam engines, this industrial revolution we have, so everything was done by like handmade. Everything we will do it by power, means power. But now we have like engines, so there is a need to have this kind of automated like power that help people to do everything. And the steam engine was one of the first things that appear or make the thermodynamics like as a science start to appear or start to try to exist. So as we mentioned in previous lecture, thermodynamics itself, this is the study of energy. Okay? So if you want to study of energy, so what you are studying will be thermodynamics. But what kind of energy? There are a lot of things about energy we can use. Thermodynamics basically focus on 2 things. The first one is conversion of energy from one form to another form in order to accomplish like any purpose that you need. So I have kinetic energy, for example. I need to convert this kinetic energy into work in order to use this work for something. If I have a fluid is moving with a very high pressure, so I need to move it to another to heat, for example. Okay, so I have different forms of energy, and I need to change these forms of energy from one form to another form. From one form that I can't use to another form that is useful for me, I can use to get a certain purpose. So this is number 1 about thermodynamics. Number 2 is what will happen to any system, and we will explain what is meant by system later. This is one of the basic concepts. What will happen to any system if we add or remove energy from the system? So how the system will respond, how the process that you are studying will respond in case of energy added or energy removed from the system. So always keep in mind, in thermodynamics, basically we are talking about 2 things. Conversion of energy from one form to another form. So the form that we are obtaining, this is the useful form. We can use this form in order to obtain electricity, in order to generate heat, whatever we have. And the other thing, if we have system, if we have process, how this system or process will respond in case of we add energy to it or we remove energy from it. Okay? How thermodynamics appeared? So it started in 1697 with the development of steam engines. So this was the first thing that it makes the scientists or the whole world know that, okay, if we have a certain form of energy, we can have another form. The conservation of energy started to appear after this time. Then in 1712, we made more improvements on this steam engine we have. And then in 1848, this is the first time the word thermodynamics started to appear. And this is by Lord Kelvin. We know Kelvin because Kelvin is one of the units of temperature measurements. Okay, so this was the first time we know that, or there is a new word in the scientific community, it's called thermodynamics. So as you can see, we have almost 50 years people were doing some things. These things are directly related to thermodynamics, but by this time, there is nothing called thermodynamics. After 50 years of the generation of steam engines and the development happening in this one, then we start to combine all of these principles together and then define a new discipline or a new field of science called thermodynamics. And let's say, and then we have the first thermodynamics textbook. This was almost 170 years ago, 1859. And this was by William Rankine. And this name was repeated a lot in the chapter 5 when we study the thermodynamic cycles and these things. So as you can see, it's something takes a lot of time, takes tens of years in order to be developed. Even we can say the thermodynamics, by the way that we're having right now, it takes more than this. Because as you remember when I explained, we have Boltzmann who start to apply statistics into thermodynamics to give better interpretation of the fundamental concepts of thermodynamics. This was in the start of the previous century. So it takes almost 140 years until we have something that related to thermodynamics without knowing this is related to thermodynamics, and then we have physical interpretation or even mathematical derivation of the fundamental laws of thermodynamics. It takes all of these years we have. And again, how it starts. So again, if we start in terms of the concepts, it starts with some early foundations. We start with Galileo. So what is gas behavior? What is the relationship between temperature and pressure? Relationship between temperature, volume, pressure, volume, and these things. Then we have classical thermodynamics. So we have Carnot. Carnot, it's also one of the names that you will read it a lot in the course. We have Clausius, we have Kelvin. So all of these scientists, they start to develop some or explain thermodynamics that is defined as classical thermodynamics. And this is something we will start also to explain. Then we have statistical mechanics. This is mainly by Boltzmann. So he tried to use the statistics in order to explain concepts of thermodynamics. Okay, so we have what is called statistical mechanics or statistical thermodynamics, which is the concept of the quantum that we have, or for sure you are hearing about this right now. Then we have chemical thermodynamics, and this starts when we have the concepts of gaps-free energy. This is one of the thermodynamic properties. Also, we'll explain in the I think in chapter 6 we'll explain it. And then the last thing that we have the concepts of equilibrium. As I said, we have quantum, so all of this modern advancement in the field of thermodynamics, and now we have a lot of advancement happening in thermodynamics. Okay, clear? So again, so this is just a brief history about thermodynamics. So it's not something that starts as the concept of thermodynamics wasn't stable from the beginning. It takes more than 100 years in order to put all of these principles, all the scientists' observations together in order to have a solid science, what is called at the end thermodynamics, which we are studying right now. Questions?
Do you think it will continue to develop into other kinds of thermodynamics?
Why not?
Yeah.
So far, a lot of, I know someone, he's got his PhD from MIT, and his idea was trying to develop the equations of states. So this would be the topic we have in chapter 7. So always there is the room that, because all of these equations that have a percentage of error or have some limitations in uses, so we still are trying to improve all of these things. Okay, and for sure the quantum and all of these things. So quantum is one of the things that I think it's still not yet discovered. So there are a lot of things that we still need to find in this quantum thing. Okay. This is why here in the PhD program there is a required course of statistical thermodynamics. So this one gives you introduction of how statistics apply to thermodynamics and introduction to understand these quantum things. Clear? Questions? Sure? Okay. Now let's start the important part that we have maybe in this whole chapter. So this term, the basic concepts and terminology, this is the most important part we have in this chapter as a whole. So again, if you miss any point in this, in any of the points that I will discuss right now, just stop me and ask me to repeat again. Okay? Make sure that when you get out today, you understand everything that we are explaining. Okay, so we have a lot of concepts, a lot of terminology in thermodynamics. We have something called systems. We have states, properties, processes, cycles, steady state, equilibrium. All of these things we will hear a lot in the course. And you should know what is meant by each of these words. So basically systems, this is one of the basic fundamentals of thermodynamics. So you should know what is meant by system. Then you should know what it is meant by the state of the system or properties of the system we have. Okay, so this is the characteristics, how we can characterize our system. Processes and cycles, this explain the actions, the patterns that is happening, the changes that is happening in the system over time. So what exactly is happening to the system? So again, we have system, We have characteristics of this system, which is state, properties. Then we have actions, patterns, changes happening to the system over time. This is cycles and processes. And then we have a steady state and equilibrium. This is a description of the time stability of the system, the force balance of the system we have. Okay? So these are the 4 terms. It's very important to understand them as systems first, state properties, processes, cycles, then steady state equilibrium. So it's very important to study all of these terminology, because if you remember, our goal from thermodynamics is to be able to design equipment, analyze the performance of this equipment, right? But in order to achieve this ultimate goal, you should start from the end. So we will start with property. What do you mean by property? State, process, cycles. When you understand all of these basic concepts, now we are ready to understand the first law of thermodynamics. Once you understand the first law of thermodynamics, we will introduce another property, which is entropy. After you understand this, then you can understand the second law of thermodynamics. And once you understand these 2 laws of thermodynamics, then you have the basics now to start with analyzing several equipment or different equipment. Okay? Okay. So let's start by explaining each one of them in detail. So system. System, this is the basis of the thermodynamic analysis. You cannot do any thermodynamic analysis if you can define your system. Okay? Because system, this is the part that you are studying, you are analyzing, or you are modeling. Okay? So this is the portion that we have to study. If you have a full factory, for example, you can analyze all of it, so the whole factory per your system. You can analyze part of it. You can analyze a single equipment. So this single equipment will be your system. So your system, whatever part that you are studying, or you are analyzing or modeling, and who are deciding the system that you will study, this is you. So you will decide what is your system. So my system will be a single unit. My system will be multiple units together, 2 units, 3 units together, or the whole thing that I will study. So let's say, for example, if I have this example, I have some water inside a bottle like this, then one can say, okay, I will select water, and this water will be my system. So I will focus on what is happening in the water itself. So now I decide water will be my system. Or someone can say, okay, I will study water and the wall of this bottle I have. Okay, so now I have 2 things forming the system, the water and the wall. Or someone say, okay, I will study water, the air I have inside. So here, as you can see, I'm excluding the air inside, but here I have the air, then I have the wall, and I have the part of the surrounding. So this will be my system. So anything that you can decide, okay? So the system, this is the part that you are studying, and this is your responsibility to decide what is the part I will study, okay? System is usually outlined by a boundary. This is the dotted line here. This is called the boundary. As you can see here in this one, as you can see in this one. So this is called the boundary. Okay. Anything inside this boundary, this is your system. Anything outside this boundary, this is your surrounding. So again, we have now 3 words that you will hear a lot. We have system, we have boundary, we have surrounding. Boundary, this is the border. Anything inside this boundary is called system. Anything outside this boundary is called surrounding, as you can see here. So this dotted line is the boundary. Anything inside system, anything outside is surrounding. When you are analyzing, when you're making a thermodynamic analysis, only you are focusing on the system. Okay. Sometimes we care about what is exchange of energy between system and surrounding, but your main focus on what are the changes happening in the system. Clear? Any question?
We do need the thing with open systems.
Yep. Okay. This will be after 2 slides we will discuss it. So again, system can be like refrigerator. Someone can study the refrigerator. It will be my system. I will apply thermodynamic analysis for this one. You can have a whole electric power plant. You can study all of it one time. Or you can study only the cooling water. You can, the cooling water system, this cooling system. I can study only the turbine. I can study only this steam generator. So based on your selection. If you have like an engine, for example, so the whole engine can be my system. So you can decide whatever that you want to study. Clear? Any questions so far? Okay. Now, how can we classify the thermodynamic systems? This is your question. So thermodynamic systems can be closed systems, can be open system, can be isolated system. Some textbooks, they said we have three categories, like open, closed, isolated. Some textbooks, they are only two categories, open and closed, and isolated is a special case of the closed. Okay? So regardless, like it's two or three, just you know that what the difference between them. So what we have here in closed system, let's start with closed system. So in closed system, what is happening? So you have your system. There is no mass from the system can go out to the surrounding. There is no mass from the surrounding can go from the surrounding to the system. So mass cannot be exchanged between the system and surrounding, but energy can. So only what is allowed is energy transfer or energy movement or energy exchange between the system and surrounding. System can lose energy to the surrounding. Surrounding can add energy to the system. But the mass is kept constant. The mass cannot change. Okay, so this is called closed system. Special case of it is isolated system. In isolated system, no mass exchange, no energy exchange. Nothing can be exchanged between the system and surrounding. The system is completely isolated. No mass can leave it, no mass can be added to it, no energy leave it, no energy added to it. Okay. The other side is open system. And in open system, we have everything can be exchanged. Mass can be exchanged, energy can be exchanged. Clear? Okay. So the classification of the different types of systems, it depends on can mass exchange between the system and surrounding? Energy can be exchanged between the system and surrounding. If both of them can transfer or exchange between system and surrounding, then we have open system. If only energy, this is a closed system. Neither one of them, this is an isolated system. Okay? So an example of open system, so we have pipes, flow inside pipes. This is an example of open system. We have inlet to the pipe, flows go to the pipe, flows goes out of the pipe. So we have mass. Also we have energy can exchange. We have compressors. This is another example of open systems. Turbines. This is open systems. Expansion valves. Open systems. Pumps. Diffusers. Like heat exchangers, nozzles. All of these examples of open system. And all of these exist in chemical plants. Okay. Closed systems, also we have a lot of examples on closed system, but closed system itself can be classified into two categories. We can have something called closed system with fixed boundary. Fixed boundary means the boundary itself is fixed, it's not a change. So let's say I have this tank, for example, and this tank is like no mass, there's no inlet, no outlet from this tank, so it's closed. And then we have like anything rotated inside here. And I decide this is my system. I have this rigid wall. So I decide, okay, anything inside this wall will be my closed system. So this wall is rigid wall, so the boundary is fixed. It's not a changing. Another example, or the other side, is moving boundary. Moving boundary, let's say if I have this piston, and I decide whatever inside this piston will be my system, then this can be my system. If I increase the level or make this, the pressure applies on the piston, like decrease, then the piston will move up. So what will happen? So we will have some expansion happening inside the system. So the system will expand. It's still there, no mass exchange. Okay, there is no input to the system. There is no output from it. Only we have some expansion happening. So now what is happening? The boundary itself expands. So this is why it's called its moving boundary. So the same mass here is the same mass here. But only here we have expansion happening to this mass because of the pressure reduction. Okay, so mass does not change. The total mass is the same. Only we have expansion. We have a moving boundary. Okay. Another also example is a balloon. So if you are studying the whatever happening in the balloon here, so if you are putting air inside or just leave it in air, for example, so it can expand a little bit. So this is another example of moving boundary. So closed system can have fixed boundary, can have a moving boundary as well. Okay. So just to summarize this, so we have three types or three terms that can describe system: isolated system, closed system, open system. In open system, both mass and energy can cross the boundary. Closed system, only energy can cross the boundary from system to surrounding or surrounding to system. Isolated system, none of them can cross the boundary. Sure.
So if we have like a
a system and it's closed, but it has a permeable surface, would we consider that an open system
Okay.
or like a closed system?
Now,
Like,
again,
say,
sorry. So you have system, closed system. Okay, and has what?
let's say like a paper cup and like we put water in it and the water can seep out. Would that be considered like an open system or a closed system?
If you have any mass added to the system, then it will be an open system.
Okay.
Okay? So as long as the total mass of the system change, so this is an open system.
Okay.
Clear? Questions? Okay. This is the first point, the first terminology we have. So what is meant by system? So system, this is the part that you are studying. System can be open, closed, isolated. Okay? So this is the most important point that I need you to remember. The second concept we will explain is properties and states. So what is meant by property? Property, basically, this is any measurable macroscopic characteristics of the system, something that you can measure. This is the key of defining property. You can describe this property as number. Okay, so it's something measurable, and you are using to describe your system, such as pressure. I can measure pressure. I can give you a number for this pressure. Temperature, density, mass, volume, a lot of properties that we can measure and we can use to describe or characterize our system. Okay? Then there is there are a lot of properties that we can use to describe the system, but only the properties that is related to energy, these are called thermodynamic properties. Okay, so thermodynamic properties, these are the properties that is related to the energy content of the system. Okay, it affects the energy of the system. Okay. The properties we have, or the thermodynamic properties, we can classify it into two categories. So the first category, we can classify system properties into something called extensive properties or intensive properties. This is one category, extensive or intensive. Then we can say properties can be state properties or path-dependent properties. Okay. So again, so now we have properties. This is something that we can measure, something related to energy, and this is something that characterizes our system. Okay. So now the key is how I can classify what is the difference between extensive and intensive. What is the difference between state property and path-dependent property? So the difference between extensive and intensive. Extensive properties, these are the properties that depend on the value of this property, depend on the size of your system. So let's say, for example, I decide, okay, I will study this system. This is my system that I will to study. So this one has a mass. Someone say, okay, I will study only half of it. So half of it will be the system. So what I change? Do you think mass will be the same? So mass will be different. So the size of the system, when it changes, the value of this property will change. So we have mass, we have volume, so all of these things depend on the size of the property. So this is called extensive property. We have other properties, intensive. Intensive properties will be the same, regardless you study the whole size to be your system, half of it. Similar to density, for example. If you have water, if you have a small cup of water, the density is 1,000 kilogram per meter cube. If you have pool of water, okay, so what will be the density of it? It's almost 1,000 kilogram per meter cube. So the density is the same, regardless of the size of your system. So now this is a property that its value is not depending on the size of your system. So it's called intensive property. Okay, so always we have extensive, intensive property. When we make thermodynamic analysis, we prefer to use intensive properties. We don't prefer to use extensive properties because we need to make our analysis or perform the analysis in terms of properties. All these properties doesn't depend on the system. So if we are studying the same thing, for example, we have same unit. So one decide to study the whole unit, one decide to study part of it, one decide to study half of it. If you are using extensive properties, then your analysis will end up with different results because of your system size is different. But if you are making your analysis by using intensive properties, then you will end up with the same result because what you are using a property that is not a function of the size of the system. So you are using small size, you are using large size, the same result here that you will end up with. Okay, so this is why we are prefer to have intensive properties. Always in the problems, in the analysis, if we have extensive property, we prefer to transfer it to intensive one. And how we can do this? Any extensive property, if you divide it by mass or by mole, so divide it by the amount of your system in terms of mass or in terms of mole, then you are converting it to extensive property. So let's say, for example, if I have V, volume. Volume itself is extensive. But if you divide volume by mass, then we have what is called specific volume. Specific volume, this is intensive. Okay. Again, volume, extensive. Volume by number of moles. So we have molar volume. Molar volume, this one is intensive. So we have extensive property, and you convert it to intensive one. So again, for the terminology, if you have any symbol have this hat above it, so this means specific. So this means this property divided by mass. If you have this underline dash, so it means molar. And molar means the property divided by moles. So this is molar volume, volume by mole. This is specific volume, volume divided by mass. Okay, so we'll use it for everything. Just give me a second. So again, so just quick terminology. V, this is the moles. N, M, this is the mass. N, this is the number of moles. All of these together are extensive properties. But when you combine them, so we define specific volume, or we define molar volume, and these are intensive properties. Okay, question.
For the molar volume, can that also be denoted with a dot above the...
You can do it, but usually you are using dot for rates, so everything divided by time. So if you can use it, it's fine. I can understand it. But then we have, in open system, we are dealing with flow rates. So now how can you differentiate between this is rate divided by time and this is molar divided by mole?
Okay. Yeah.
I know that textbooks are using different technology.
Yeah.
So sometimes it may be confusing. So this is why I'm trying to keep it as clear. If you did in the exam, for example, I can understand. So based on the logic that was there.
Since mass is an extensive property, can it be divided by mass itself into an intensive property, or does that one like not exist?
Okay, now divided by manner, they will end up with 1.
Yeah.
That is constant.
Yeah.
And then you cannot change it. And the definition of property is something like measurable quantity that characterizes the system. So how do you characterize the
That's
system?
not what it's property anymore.
Okay. So at least it will end up with a constant. Okay. Questions? Clear so far? Okay, here we have table. This table gives you some examples of intensive, extensive properties. So we have volume, extensive. We have specific volume, intensive. We have mass. Density is not equivalent to mass. But this is in the table. We have enthalpy. We have a specific enthalpy, which is enthalpy divided by mass. Internal energy, specific internal energy. So entropy. Kinetic energy, this is extensive. Potential energy, extensive. We have for sure temperature, pressure, specific entropy. So all of these intensive properties. Okay. So this just shows you the like examples of these properties that you will see in a lot of other problems in the course. Okay. Let's see the other category. Now we know that we have properties. We know what is meant by properties, and we know that properties can be extensive, can be intensive. Okay. Now the other category, properties can be state or path dependent. So what is meant by this one? State properties. These properties are described by the conditions, like at a particular moment, and independent of how the system reach this condition. Okay, similar to temperature, pressure, internal energy, enthalpy, entropy. So what this means? Let's assume that I have this diagram, and I tell you I have like system at this condition. Let's assume the y-axis, this is the molar volume, x-axis is temperature. So I have my system at this point. So my system is at a certain temperature, T1, have molar volume, V1. Then I have some changes happen to this temperature. Maybe I add energy to it, remove energy to it, so whatever happened. So we have some changes happen to this system. So this system change, and the final condition becomes this point, which is T2 and V2. Now, when I ask you, okay, we can reach, and we can go from this point to this point by different ways. Okay, and this is something will be discussed later, but let's make it simple. We can go through this black line, which is red right now. We can go through here. So we have some change at constant molar volume, then we are making changes at constant temperature, for example. Or we can increase the volume, then change the temperature, then change the molar volume again to this point. So there are different ways that you can move from the initial point to the final point. But do you think that the way of this movement, of the way of changing from point 1 to point 2, will it change the initial or final conditions? So T2 will be the same, right? Regardless, you are going from the initial to the final point by this path, or this path, or this path. Regarding of your path, regarding of the way that you are moving from point number 1 to point number 2, the conditions at point number 2 will be the same. There is no difference. So this is what it's called the state properties. It doesn't matter how you move from point number 1 to point number 2. At the end, I want to know that what is the conditions at point number 1, what is the conditions number 2. What is happening between 1 and 2, this doesn't matter. Clear? Questions? Okay. So this is called the state properties. And also I can tell you, this is something that we can see, but you can also calculate like delta T for this path. This will be the same as delta T for this path, the same as delta T for this path. So even the property difference between these 2 points will be the same regardless of the path that you are having. So if you have something like this, so this is a state property. And again, temperature, pressure, internal energy, enthalpy, entropy. So all of these lies in this category. Clear? The other one is path-dependent properties. Path-dependent properties, this will be the other side. The value of the property depends on the path. How you move from point number 1 to point number 2. Based on this path, the value of property will change. Let's take example for this one. So let's assume if I have this piston, for example, and this piston initially was at this position at point number 1. So we have here point number 1. This is my initial position. Then you are reducing the pressure for this piston. This piston is going up from point number 1 to point number 2. So you can go from point number 1 to point number 2 in a certain path. Okay, someone say, okay, instead of reducing the pressure, I will increase the temperature of the whatever working fluid, so we'll have the piston will expand, right? So the piston also will move from point number 1 to point number 2, but the movement will not result from the pressure reduction, but the temperature increase. Make sense? So now you are doing the same thing. You are moving from point number 1 to point number 2, but with different mechanism. So this is why you can have different lines that can describe the way that you are moving from this point to another point. Two properties that are considered the path-dependent functions. The first one is heat. The second one is work. And this is why, because when you calculate heat and work, they are calculated by the area under the curve. So let's say if you are at point 1 and you are moving at point 2 and you take this path, so you go first here down and then you go to the left. So what is the area under the curve? This is gray area. So only this gray area representing the amount of work done by or on the system to move from point 1 to point 2. But if someone at point 1, which is the same at this point here, and say, okay, and here we have point 2, for example. So someone can say from point 1, I will go here, and then I will go to this way. So now he has different path. So the area under the curve will be this gray area. So the work will be different. So heat and work, these are path-dependent properties. It relies on how you are moving from the initial point to the final point. The way that you are moving, it affects the value of this property. Clear? Questions? Any questions? Again, so we have properties, or let's start from the beginning. So we started with systems, remember? So this is the part that we will be analyzing. Systems can be open, closed, isolated. Then we have properties, measurable quantities that characterize the system. Properties can be state, functions can be path-dependent functions. Properties can be extensive, can be intensive. Clear? Any questions so far? Okay. As we said, we have a lot of thermodynamic properties. any thermodynamic property either can be measured, that you can measure with very simple like experiments, or it's a fundamental property. We can have fundamental laws that we will describe in next chapters. Fundamental laws that we can use to calculate this property, or properties can be derived property. So the measure the property similar to heat capacity. This we will discuss in chapter 2. We have temperature, we have pressure, we have density. Density is mass over volume, and we will just give you a quick reminder of how we can calculate these things. Then we have fundamental properties, which is internal energy, entropy, and this is the chapter that we will see each one of them. Okay. Then we have derived properties, so we have enthalpy, Gibbs free energy, Helmholtz energy. So this is the whole thermodynamic properties we will study, and in each chapter that you will see each one of them. Okay? Questions so far? Clear? Okay. So let's start with the basic ones: temperature, pressure, density. So that's something that you know from previous courses. Just a quick reminder. So you know that temperature, we can define it with different scales. There's Kelvin, Celsius, Fahrenheit, Rankine, and the relationships between them is this one. So temperature in Celsius is Kelvin minus 273, Fahrenheit is 1.8, temperature in Celsius plus 32. And when you like have a problem, make sure that you are measuring the temperature or temperature difference. Because if you have, let's say, temperature, you have T, it's 25 degrees Celsius, and I ask you what will be the temperature in Kelvin. So what you will do is that T is 25 plus 273, so you will say the temperature will be 289 Kelvin. So this is the absolute temperature value. But if you have an example, and I'm telling you that delta T, temperature difference, is 1 degree Celsius, so what will be the temperature difference in Kelvin? Exactly, it will be 1. Okay, so the temperature difference is the same, but the temperature is changing. So always make sure of this. Okay, don't confuse or don't get confused with these things. So this is like a quick thing that you need to remember about temperature. Then we have pressure. As you know that we have 3 things of pressure. We have absolute pressure, we have gauge pressure, we have vacuum. So the relationships between them, the value of the pressure above the atmospheric pressure, this is what is called gauge pressure, which is here, the gauge pressure, the pressure value above the atmospheric. Then we have the vacuum, the value of pressure below the atmospheric pressure, and the relationships between them is that the absolute pressure, this is the atmospheric pressure plus gauge, and the atmospheric pressure is the absolute plus the vacuum. So always keep this in your mind. All the instruments that we are using to measure pressure, they are measuring the gauge pressure. So let's say if you have like a pressure gauge and the reading is 0. So does it mean that the pressure is 0? Or it means that the pressure is atmospheric? So again, we call this equation. Absolute pressure is atmospheric plus gauge. So put it here. So we have absolute pressure. This is the atmospheric pressure plus gauge pressure. This gauge pressure, this is what is measured by pressure gauges. So most of the pressure gauge instruments are measuring the value of the gauge pressure. So if I give you this one, this instrument here, for example. So you have this one, you fix it on a pipeline, for example, and it gives you a reading of 0. So this means the working fluid inside this system, does it have 0 pressure, or the pressure is equivalent to the atmospheric? Atmospheric. So if this is 0, so this means the absolute pressure, the actual pressure inside the system, this is the atmospheric pressure. Clear? Clear? Any questions? Okay. Again, you have pressure gauge. You put this pressure gauge on a unit, for example, and the reading is 400. So does this mean that the actual or the absolute pressure is 400? No, it means that it's 400 plus the atmospheric pressure. Okay? So always remember this one. And for sure, remember that the relationship between pressure and the altitude is inverse. So as you are going up, the altitude increase, the value of pressure like decrease. Okay? Questions? The last part, also I need to remind you, because you will use this set of equations a lot of the problems, which is the density calculation. So we have density is mass divided by volume. If you are dealing with open systems, you usually have mass flow rate, volumetric flow rate. So we have m dot, mass rate, divided by v dot. This is the dot that you are asking about, right?
Yes.
Okay. So this is dot, usually we are using it with rates, if the property divided by time. Okay. Also, density can be calculated if you have information available about something called specific gravity. Specific gravity of any substance is the density of this substance divided by density of a reference. And this reference is water, which density can be 1000 kilogram per meter cube, 1 gram per centimeter cube, 62.43 pound mass per feet cube. Different system of units, remember? We have SI system, American system from previous lecture. So we can also use this formula, specific gravity formula, to calculate density. Volume is nothing but area times length of the, like any system you have. Volumetric flow rate is volume divided by time, or area and volume. We know that it's area times length, so it can be area length divided by time, length over time. This is velocity, so the volumetric flow rate can be area times velocity. Just very basic equations that you will use in a lot of problems we have in the course. Clear? Any questions? And again, this is just table. This is just if you can just read it. We will discuss it while you are going in with the semester, but this is the description of the properties. Is it intensive or extensive? The relation that we are using, if this property is derived, for example, and how can we classify this property? This is just for reading, just to get you familiar with the properties that we are expecting to see in the course. Okay? Any questions so far? So now we have discovered what is meant by system, what is meant by properties, and then the last part here is to describe the state of the system. So in order to describe a thermodynamic system, we need to describe, or what is the state of the system. Okay, we describe the state of the system by finding the values of the properties. So you just, if you can say, I have this system at this temperature value, at this pressure, at this enthalpy, then all of this group of properties, by putting them together, so what you are doing is to describing the state of your system. So let's say, for example, I have here one system. This is my system. Mass of this system is 2 kilogram. Temperature 20 degrees Celsius. Volume is 1.5 meter cube. So this is state number 1. If I have some changes happen to this property and to move to this one, mass is 2 kilogram, 20 degrees Celsius, volume is 2.5 meter cube. This is a different state, because we have at least one value of the properties change. So if you can compare the properties here, they have the same mass, they have the same temperature, but they have different volume. So since they have different volume, so they have two different states. You cannot describe these two cases as like one case, or you consider both of them as the same thing. Okay. So if you have a change in at least one of the properties, then this means you are moving from one state to another one. Clear? Okay. How we can, like, let's say if you have two states and you are moving from one state to another one, this is called by like a cycle or a process. This is called by a process, not a cycle. So I have, let's say, my piston was here. So I have all my system takes all this area, so the volume is V1. So now I compress the piston, I reduce the area, so this is my final states at V2. So the way I am moving from state number 1, the initial state, to state number 2, the final state, this is called a process path. My path, okay, or my process, the process that happened, the change I have in the system. And this change can happen because of a lot of things. Because we have mass exchange happens, we can have energy exchange happens, energy added, energy removed from the system. Okay, we have internal transformations that also may happen. So anything can cause it. Exchange of mass, exchange of energy makes your state change from one state to another one. And again, the way of this change of the states is called the process path. Again, one example. Here we have, this is the example I said. So we have piston, and then you compress the piston. So we have a process that you change from one system to another one. If you have open system, so usually in open system, the inlet has different conditions, different state. The outlet has different states. So all the open system is considered a process. Okay, because the inlet and outlet are at two different states. So the whole open system is considered a process. Okay, so again, the process is describing the path between state number 1 and state number 2. But usually in thermodynamics, when you study systems, system will not have like a single process path. It can have multiple. So this is why you can have system at this state, then it move to state number 2, then it move maybe to state number 3, then move to state number 4, and stay at state number 4 as your final state. Or as in this figure here, it can move to state number 2 and then go to state number 1, for example. Okay, so usually you have like series of processes happen. The final state and the initial state, not necessary to be the same, but sometimes be the same. And if the initial and final states are the same, similar to this one, so I start at point 1, at the end, I end at point 1. So now this process we call cycle. So cycle is a special case of the process. So process, this describes the change, in general, the change happening between a state to another state. The cycle, this is like a process that consists of series of stages or series of processes, but whatever initial state, this will be the same as your final state. So it is this one here, for example. I have this piston at state number 1. So then I compress the piston. I move to state number 2. Then I have some changes happen. I move to state number 3. Then I have other changes happen. I go to state number 4. From state number 4, I return again to state number 1. So if you put this diagram, for example, you can represent it by something like this. From 1, I go to state 2. 2, I go to state 3. Then I go to state 4. And then from state 4, I end up at state 1. Final and the initial states are the same. So this is called cycle. Okay? So again, just quick summary. We have system, open, closed, isolated. We have properties, measurable quantities, can be extensive, intensive, state or path function. Then we have process, that the change that is happening in the system from one state to another one. Special case of the process is the cycle. And when the process is called cycle, if the initial and final states are the same. Any questions? Okay. Last thing that we'll explain, as we said, we have the process, it describes the changing happening to the states. So just a quick names. Your system may have some changes. So the states can change at constant temperature. So, and in this case, this change or this process will be called isothermal. So when you hear this word isothermal, it means there are some changes happening, but these changes happen at constant temperature. Temperature is the same. Or we have changes can happen, but the pressure will be the same. And if this happens, so the process will be called isobaric. Again, changes may happen at constant volume. And if this happens, your process will be called isochoric. Again, changes occur and entropy will be the same. So this is called isentropy. So usually in the problems, I can give you some numbers, but in the description of the problem, I tell you we have an isothermal process. I didn't mention anything about temperature. Then you should know that isothermal means the initial and final temperature are the same. Okay? The process is isobaric. So I'm telling you that we don't have any changes in the pressure in this problem, for example. Clear? So it's very important to know what is meant by each of these words. This will be repeated a lot. So sometimes we have changes happen in the process without exchanging heat, and this is called the adiabatic. So when you hear this word adiabatic, so this means there is no heat added to the system or heat removed from the system. There is no energy exchange. But these two terms also will explain in, I think, chapter 4, what the difference between reversible and irreversible. So your process may be adiabatic and irreversible. So this is called adiabatic. So when you hear this word adiabatic, so it means the process is irreversible and there is no exchange of heat. It's isolated. No heat added, no heat removed. And the process itself is irreversible. So this what should come to your mind when you hear this adiabatic. But let's say if there is no heat exchange and at the same time the process is reversible. if the process is reversible and adiabatic, so it can be called reversible adiabatic or isentropic. So again, there is a link between these two types here. So if you have reversible and you have no energy exchange, so the process is reversible adiabatic, and reversible adiabatic it can be isentropic. Okay? Is it clear? Any questions? Sure. Okay. So the second quiz, it was supposed to announce it today, but I didn't cover the part that I need to cover. Then I will postpone it, so there is no need